Hi guys, morning everyone. Welcome to the session and welcome to the India's most comprehensive preparation platform, that is the BYJU'S Exam Prep, and a happy Sunday all of you. And yes, let's come up on this Sunday and discuss one of the very important topic of digital circuits. As you know, the champion series is going on. Yes, the live gate workbook where we are covering more than 500 technical questions of your branch. Yes, you heard me correct. Okay, more than 500 technical questions. As a practice on the YouTube, we are coming up daily live with different topics and different subjects. This is the third topic in digital circuits that I am taking. Okay, and that is the sequential circuit. So it's a question practice, but of course through question practice you learn miscellaneous things, you learn miscellaneous concepts. So stay tuned. Let's learn a variety of questions based on sequential circuits, including flip-flops, counters, shift registers, and etc, 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 state diagrams, and all those things going to come up for you. Correct. Just a second. Yes, come on. Okay, you've sent me an Instagram. Yeah, I'll confirm you today, Prince. Need not, I'll confirm you today. Okay. Yesterday after the session I could not check maybe Instagram and all. Today after completing the session, morning I woke up, then I was preparing this PPT and all for you. Today after the session I get free, I'll look back into your query, Prince. Okay, I told you yesterday also in the session, so don't worry, I'll look back to your query. Let us get started then, guys. Just a second. Okay, chalo guys, all ready? Let us, hi, good morning, ABD, Tushar, Prince, Abdul. Okay, so guys, let's get moving ahead. This is a brief intro about me in case somebody new to my classes. This is your mentor and educator Rakesh. I have secured All India rank 9th in GATE, completed my masters from Indian Institute of Science, Bangalore. Right, and it's been more than 12 years, having trained more than 50,000 students. I'm dealing with these particular subjects for you. Okay. Yes guys, once again a quick reminder that Tuesday is just coming, day after tomorrow, 6 September 8 PM. The BYJU'S Exam Prep presents you a free important workshop on its app, that is the BYJU'S Exam Prep app that you can download from the Google Play Store, where we'll be talking about anybody can ace GATE. But do you know how? Yes, everybody and anybody can ace GATE, but how? Yes, the expert Ravinder Thube Sir, MTech from IIT Kanpur and All India rank 79 is GATE, is going to come up with fantastic approaches for the GATE examination, so that you know anybody can be really acing the GATE examination. Okay. Payash, see usually yeah, good morning Payash and Rahul. VLSI, the timings are usually for this champion series for EC is going on in the evening, but since today is Sunday, we have planned this at 12 PM. Sunday everybody is comfortable in the morning. Okay, so let's get started guys. Question number 1 here on your screen. The question number 1 here on your screen, the expression for next state Q plus in the following circuit. The expression for next state Q plus in the following circuit. So this is what is a SR flip-flop. And of course we know SR flip-flop has one fundamental problem. SR flip-flop has one fundamental problem, that both the S and R inputs cannot be high at the same time. And that is why the inputs that are fed here is the complement of each other. Okay, if suppose this is what is X, then this will be X, the above one will be X bar. Okay, so if the output of this gate is X, R get X, the S will get X bar, they are complement of each other, so both cannot be high at the same time. Okay, now what is the expression for next state? So now if I talk about the SR, what is the expression for next state actually? S plus R bar Q, I hope you all remember. SR flip-flop, the next state equation is S plus R bar Q. You must remember these points, okay? So S plus R bar Q, and if not, we'll come up with different questions revising all those things. Okay, good afternoon Teju, Divya, Sonali, very good afternoon all. Okay, now what is the value of S here? What is the value of R here? So R is getting this value, which is the output of, let's not call it as X, X is already here. I can give any name here, W Just wanted to show you both are complement of each other. So what is the value of R? R is getting the signal W, which is the output of the XNOR gate, and X XNOR Q, right? What is the value of S? The S is getting the complement of it, and what is the complement of XNOR? Is the XOR. So let me put here S is equal to X XOR Q, everybody, plus R bar. So R is XNOR, R complement will again be XOR, multiplied by Q. So very simply, X XOR Q is common. Then you are left with 1 plus Q. 1 plus Q in Boolean is equal to 1. So my answer is X XOR Q. My answer is option number C. So can I say that, let me ask you a simple question. If the answer is X XOR Q, this particular SR latch along with this inverter and XNOR gate behaves as what flip-flop? So you are given a SR flip-flop. The question can also be this. The question can also be something like this. This circuit behaves as what flip-flop? It is a SR flip-flop. It is a SR flip-flop along with some logic circuitry, but eventually it behaves like which flip-flop? Can anybody come and tell me? Q plus is equal to X XOR Q. Q plus is equal to X XOR Q. What is the equation you are getting? Q plus is equal to X XOR Q. Tell me. It is the next state equation of which flip-flop, guys? Come on, everybody try to recall. It is the next state equation of which flip-flop? Perfect. It is the T flip-flop actually. Okay, it is just like T XOR Q. It is T XOR Q, and it is the next state equation, characteristic equation of, it is the characteristic equation of T flip-flop. It is the characteristic equation of T flip-flop. It is the characteristic equation of T flip-flop. Okay, guys? Yes. So this question can also be, the following circuit behaves as what flip-flop? It is going to be T flip-flop. Okay. Let's move ahead to the next question. Okay. And this is a very similar question. So this is your homework number 1 for today. I keep giving you 3-4 homeworks in the classes, and guys, the homeworks of past 2 classes, that is the logic gates and minimization, class number 1. Second class was combinational circuits. I have given you several homeworks, 6 homeworks in the first class, 3 to 4 homework in the second class. The answer of the homeworks have been posted in the comment box. You can check your answers, you can match your answers. I repeat, the answer of the homework questions of the previous 2 classes have been replied in the comment box of those videos. You can just go and check the comment box, you will get the answers. This is your homework number 1 for tonight, and for any of the homework, this is a simple one only. Do not comment your answer in the live chat box. Please do it in the comment box after the video gets over. Okay. Thank you, ABD. Chalo guys, let's come here. The following circuit represents what? The following sequential circuit is what? What type of flip-flop it is? And if you are not aware about what is a reset dominant flip-flop, I'll explain you that. Reset dominant flip-flop. I'll tell you basic theory about that. But first, let's come to that. This circuit behaves as what? This following circuit behaves as what? So see, we can just make a, it's a mux, na? It's a 4x1 mux. It's a sequential circuit, try to be implemented as mux. Dekho. Just make the truth table actually. You just make the next state table. Just make the next state table. My input will be considered as the select line XY, and my output is Z plus. The output of the circuit has been represented as Z. So what is the next value of Z plus? So these 2 select lines will have 4 possibility. So it's a good combinations, including mux and building some flip-flops or type of sequential circuit. Now we know that if the select lines are 0, 0, what is selected? I naught, and what is there at the I naught? It is equal to Z. So the next state of Z is equal to Z. Matlab same state condition. If it is 0, 1, then what happens? 0, 1 pe I naught, 0, 1 pe I naught, and that is equal to 0. 1, 0, 1, 0 is listed here. So which input of mux is selected? 1. Next is 1, 1. 1, 1 pe what is coming? The complement of Z is coming, right? What is this? This is the complement of Z. Now tell me what type of circuit is this? No, how is it the SR flip-flop? If it is SR flip-flop, the inputs 1, 1 are invalid. They do not produce the toggle state. What is this? 0, 0 same, 0, 1 reset, 1, 0 set, 1, 1 complement toggle state, 1, 1 toggle state. And that is exactly what a JK flip-flop also does. That is exactly what a JK flip-flop also does. This is the same next state table as a JK flip-flop. Next state table, or we also call it as characteristic table. Characteristic table, right? 0, 0, output remains same. 0, 1, reset. Okay, I'll write down. It's like 0, 0, same. 0, 1, the device will reset. 1, 0, the device will set. 1, 1, the device will toggle. That is what a JK performs. Acha, what about SR? 0, 0, device remains in same state. 0, 1, reset. 1, 0, set. 1, 1 is invalid state in SR. Now, okay, the question is solved. The answer is JK, no problem. Your question is solved. Your part is over B. But what is this reset dominant flip-flop? I'll tell you. What is this reset dominant flip-flop? Oh, just wait a second. Let me change the color of the background. What is this reset dominant flip-flop? Reset dominant flip-flop, also known as reset dominant SR flip-flop. So it is a flip-flop. It is a flip-flop which has the following characteristic table. 0, 0, it is almost similar to a SR flip-flop. 0, 0, same state. 0, 1, 1 is R. R means reset. The next state is reset. 1, 0, 1 is at place of S. S is set. So next state is set. 1, 1, which is known as invalid state in the SR flip-flop. It is modified such that when the both inputs are same, the device is reset. Reset dominant SR flip-flop. When both the inputs are 1, 1, okay, we have to modify SR latch such that when both inputs are 1, 1, the device is reset. This particular logic circuitry will be known as the reset dominant. So it is just coming in the option. That is why I mentioned to you. That is why I just mentioned to you. Okay, guys, moving ahead to the next question. Moving ahead to the next question. Now see, it's again a good question, including a flip-flop along with a multiplexer, and then asking you the state diagram, and since it's an important topic, 1 or 2 gate questions I am discussing here. See, in any of the previous sessions we haven't discussed gate questions. Today also we are not going to majorly discuss gate questions, but since sequential circuit is a crucial part, so just 2 or 3 good gate questions we will discuss. Rest all will be fresh questions for you. Like all these are, you know, some different unique questions for you. Okay, we'll go to our even better questions. Okay, chalo. आ जाते हैं यहाँ पे. GATE 2019 2 marks question. The state transition diagram for the circuit shown. The state transition diagram for the circuit shown. Okay, so let us see this circuit individually. Now this is a 2:1 marks, right? Right. So there will conditions for reset. Yeah, condition reset dominant itself means that condition given both the inputs are 1, 1, the device should reset VLSI. Okay. Yes, come to this point. Okay, let's say the output of the multiplexer is Y. Okay, so what comes here? Y, and one of the thing that is coming here is Q. So the output of the NAND gate, is Y into Q whole complement. Y into Q whole complement. Now, the state transition diagram has been drawn with respect to the input A. What is there? The input is given as A. A is the select line of the multiplexer. A is the select line of the multiplexer. So dear students, if A is equal to 0, what is the value of Y? What is the value of Y? ध्यान देना. Y is the output of multiplexer. So at A equal to 0, you get I0, but I0 is equal to Q complement. Similarly, when A is equal to 1, what is the value of Y? Y gets I1, and what is coming at the I1 is Q. This is what is noted. Now, let us talk about the state transition diagram, which is going to show the transition of the state. Transition of the state means what is the next state? If the current state is Q, what is going to be my next state? That is the transition. So Q plus is equal to, it is a D flip-flop. It is a D flip-flop, and in the D flip-flop, Q plus is directly equal to the D input. So Q plus is equal to D. But what is the D? D is Y Q whole complement. But what is Y? What is Y? Y may be Q bar or Q. So dekho, there can be 2 cases here. Y is equal to Q bar. So Q bar Q whole bar provided A is equal to 0, or if A equal to 1, Y can be Q. So Q into Q whole bar if A is equal to 1. Solving this, I am getting next state is equal to, everybody listen to me, solving this I am getting next state is equal to Q bar into Q is 0, 0 complement is 1, so it is going to be 1 if A is 0, and Q into Q is Q, so whole complement will be Q bar. So if A is equal to 1, there will be toggle. If A is equal to 1, it is going to be set. It is going to be set. Now what is the state transition diagram? So we have two states, reset and set. We have the two states 0 and 1. So we have two arcs, or we have two nodes here for Q equal to 0 and Q equal to 1. Whenever the input is 0, the next state is going to be 1. Independent of the current state, the device will be set if the input is 1. What if the input is 0? Sorry. So if the input is 0, listen to me. If the input A is equal to 0, if I am at 0 state, I will go to the 1 state. But if I am at 1 state, I will remain at the 1 state. I will remain at the 1 state. Okay? I will remain at the 1 state, because anyways next state is 1. I am at 1, I will remain at 1. So arc directed to the same state. But if the input is 1, my next state is Q bar, that is toggle. That is toggle. So if I am at 0, I will go to 1. The same arrow can be used here. And if I am at 1, I will come to 0. I will come to 0 for the input 1. So here input A equal to 0 comma 1. This comma represents means for both the inputs, whether it is 0 or 1, the transition is similar. Now let us check the option, guys. Let us check the option. What is the option that you are able to match? See, usually we can write by comma. They have taken two different lines, so that is not required. The correct thing that is matching with our calculation is clearly option number C, guys. Option number C, right? 0, it goes to 1, whatever may be the input. Have a look into this, whatever may be the input, right? At 1, if the input is 0, remain at 1. If the input is 1, toggle. If the input is 1, toggle. If the input is 0, remain at 1. Okay. So it's not compulsory to show two arcs like they have shown. We can take a single arc and write down the inputs by placing a comma. That is also well justified, and that is actually a better way. Let's move ahead to the next question, guys. Let us move ahead to the next question here, ready for you. This again some state diagram based flip-flop question. Okay. The state diagram based questions are also important for gate examination. Consider the following state diagram and its realization by a JK flip-flop. The combinational circuit generates J and K. The combinational circuit given here is going to generate J and K in terms of X, Y, Q, the Boolean expressions for J and K. Now what is given to you? This time you don't have to draw. Okay, this time you don't have to draw. This time you don't have to draw the state diagram. They have given a state diagram. From the state diagram, you have to see what should be the circuitry, what should be this combinational circuit to produce the JK. Can I read the state transition diagram? From the state transition diagram, actually, let me make the state transition table. Then the story will be very simple. From the state transition diagram, let us make the state transition table, and here it is I make. Okay. Here it is, I make the state transition table. The arrows, the values written on the arrows, you know, is the inputs. Okay, the inputs is XY, right? If XY, what is the condition you are able to see? If XY is 0, 0, same state. If XY is 0, 0 or 1, 1, you remain in the same state. चलो इसको लिख लेते हैं. If XY is 0, 0 or 1, 1, Q plus is equal to Q. Right. Second point that I am able to note from this diagram, that whenever XY is equal to 0, 1 or 1, 0. देखो ना, XY is 0, 1 or 1, 0. Here also 0, 1 or 1, 0. So for both of this input combinations, 0, 1 or 1, 0, guys, your state is toggled. 0 becomes 1, 1 becomes 0. So you have the toggle state. So Q plus is equal to Q complement. Okay. So on the basis of this, now what is the tabular information? Okay, I'll write down XY and I will write down the Q plus. Acha. I will write down the Q plus. And what is that? 0, 0, 0, 1, 1, 0, 1, 1. Right. 0, 0 pe same state. 0, 1 pe toggle. 1, 0 pe toggle. 1, 1 pe same state. That is what is the information I have obtained. But the state transition, the state is actually stored by the flip-flop, we all know, and the state change will depend on the input combinations you apply on the flip-flop. So what is the input to the JK flip-flop for this state transition? So there you have to add your knowledge. What should be the JK value to get the state transition? Q plus equal to Q same, and same state is obtained when JK is 0, 0. Got this? Yes, VLSI, correct. Now, Q plus equal to Q bar for these two input combinations, but Q plus equal to Q bar is toggle, and toggle occurs when the JK is 1, 1. When the JK is 1, 1. The toggle occurs when the JK is equal to 1, 1. So what should be the value of J? What should be the value of J? Right, the J is equal to 1 when the XY is 0, 1 or 1, 0. 0, 1 or 1, 0. That is the XOR combination. That is the XOR combination. That is what? XOR combination. Okay, so that is X XOR Y. Similarly, K is equal to 1 at the 0, 1 or 1, 0. That is also X XOR Y. So both the J and K should be equal to X XOR Y. So this combinational circuit actually, is nothing but it is actually one XOR gate. There is no requirement of the Q, and the same XOR goes to both J and K. This combinational circuit is nothing but a simple one XOR gate. Okay, so the correct answer is XOR XOR option number D. The correct answer is XOR XOR option number D. Okay. Option number D. X XOR Y is the very correct answer. X XOR Y is the very correct answer for you. Now we move on towards the next question, guys. Now we move on towards the next question coming up here. Okay. Chalo. Let's take up the next question here. Yes. Again a good question. Again a good question here. Consider the following circuit involving a positive edge triggered D flip-flop. Involving a positive edge triggered D flip-flop. Consider the following timing diagram also, which is given here. Let AI represent the logic level on the line A. AI represent the logic level on the line A. In the ith clock period, let A dash represent the complement of A. What is the correct sequence on Y over the clock periods 1 through 5? Over the clock periods 1 through 5. Okay, let's have a look into this diagram clearly. Okay, AI is the logic level at A on the ith clock period. X ka value is given. Now you just have to see. So when it is the first clock cycle, this one is first, second, third, fourth, fifth, right? And the D flip-flop is positive edge triggered. Positive edge triggered flip-flop. Okay, so we have to mark the positive edges here because the transition will occur only at the positive edge. The transition will occur only at the positive edge. Now please see. Okay, at the first positive edge, what is the value of X? What is the value of X? X is equal to 1. Agar X ka value 1 hai, so what goes here is 0. This is 0. This is 0. And what will come here is A. A plus 0 is A. Okay, dekho, so what will happen? If X is equal to 0, not 0. If X is equal to 1, I repeat, the complement is 0. So output of AND gate is anyway 0 if single input is 0. This comes to the OR gate, second input is A. This is A into 1, which is A. And this is A plus 0, that will be A. So I can say that when X is equal to 1, Q plus is equal to D, but D is equal to A. So the next state of the device will be equal to A. If X is equal to 0, then what is the condition? Chalo, isko dekh lete hain. So if X is equal to 0, so this is A into 0. So there is no role of A. That becomes 0. X is 0, its complement is 1. So what is coming from here is Q bar. So you have Q bar into 1. This is Q bar. Now, so what is coming up here? Q bar plus 0, and that is Q bar. So the next state will be Q plus equal to D, but D is equal to Q bar. The next state will be toggle. Okay, when X is equal to 0. On the basis of this, let us write down what Q plus is going to be. So see here, X is equal to 1. Whenever X is equal to 1, next state will be equal to A, and this is the first clock cycle. Okay, this is my first clock cycle, and first clock cycle, the value of A, right? The value of A. Okay, the value of A, actually your first clock cycle to start hua. Okay, what is the value of A read before the clock cycle? What is the value of A ready before the clock edge? It is going to be A0. So the first thing that you get is A0. A ka value likh dete hain, chalo. Let me write down the value of A also. this is A0 here. Then in this cycle it is A1. Then here it is A2, A3, A4. On the ith clock period it is AI. So 0 pe A0, then A1, then A2 and etc. So now I'm going to write the Q plus, that is the next state, and this is the first clock edge. This is the first clock edge where x is equal to 1, and if the x is equal to 1, Q plus will take the value of A, so that is A0. Right. Next, what will come at the next clock edge? So next clock edge, x is equal to 1. X is going to make a transition to 0. Listen, x is going to make a transition to 0, but what is the value x selected? The value which is ready before the clock edge. Okay, this is the ideal transition. Okay, actually for this transition to occur, there will be some time involved. Okay, so what is the value that the device is going to read at the clock edge? It is the value ready before the arrival of clock edge. And that is what, बहुत detail में जाएंगे, तो this is related to the setup and hold type combination also. Okay, let me write down here, the x is equal to 1, and if x is equal to 1, the output will be again A. Which A? A1. Now here what is the value of x? Here the value of x is equal to 0. Here the value of x is equal to 0. ये 0 है, and whenever x is equal to 0, next state will be complement of the previous state. So previous state was A1, this has to be A1 bar. Previous state was A1, this has to be A1 bar. This has to be A1 bar, right? This has to be A1 bar. Now next, again x is equal to 1. Again x is equal to 1, so value of A will be selected, that is A3. Again x is equal to 1, so value of A will be selected, that is A4. So look into this, A0, A1, A1 bar, A0, A1, A1 bar, A3, A4. A0, A1, A1 bar, A3, A4, option number A. A2 will be skipped actually, right? Yes, Mohammed, in the PSUs there is no role of the college. Now it is all about performance, and even tier 2, tier 3 college. See, GATE has no relation with tier 1, tier 2, tier 3. It has the relation with your technical knowledge, with your efforts, with your hard works. Okay, and several tier 2, tier 3 engineering college students have got single digit or double digit ranks also in GATE. So you are eligible, 110%. Okay, so correct answer is A. It's a very good question based on the timing analysis. It is a very good question based on the timing analysis. Any confusions, any doubt, please ask me. Anyways, for the solutions, you can again refer to the PDF I am going to share you in the Telegram group anyways. Okay, with the password protection as always, but I am going to share you the PDFs in the Telegram group. Chalo, one logical question, aptitude question. One logical aptitude question, everybody. If a counter having 10 flip-flops is initially at 0, what count will it hold after 2060 pulses? What count will it hold after 2060 pulses? What count will it hold after 2060 pulses? Tell me. What count it is going to hold after 2060 pulses? A counter is having 10 flip-flops and it is initially at 0. Ab dekho, if it is having the 10 flip-flops, na? If it is having 10 flip-flops, so what is the mod number? Modulus, or simply known as the mod number. It is the total number of states. The total number of states for a counter having 10 flip-flops is 2 raised to the power 10, that is 1024. That is known as the 1024. Okay, so modulus or mod number of this counter is the 1024. This is known as the 1024. Okay, sir? Yes. Now, this is initially at 0. What count it will hold after 2060 pulses? So, its count will repeat after 1024 pulses. So, if I baat karun start ki, it is starting at 0. So, after 1024 clock cycles, it will again be 0. After one more round, that is 2048, it will again be 0. So at 2060 pulses, it is going to be how much? So how much is the difference between them? It has to count the 12th value. It has to count the 12th value. Isn't it a very logical aptitude question this is? So how many clock pulses are going ahead? 12. So it has to count the 12th value, and 12th value means 1 1. Binary mein given hai, so 12th value is 1100. Now you can convert it into the 10 bits. You can convert this into the 10 bits. Actually 1100 is the answer. Rest 6 will be, MSBs can be placed as 0. So the correct answer is option number A. The correct answer is option number A. A simple aptitude, logical question. Nothing great here. Okay. Acha. Now since I'm moving into the some basic logical question tha, now we're also going to deal with some counter based question. But let me tell you one thing. In the counter based question, there will be either the count patterns, or there will be some questions based on the clock frequency. There will be some question based on the delay of synchronous counter, ripple counter. Especially MSQ questions can be made out of there. What are the type of MSQ questions? I'm going to show you. I'm going to show you the MSQ questions also based on that. A quick revision. Let me just have a quick review. If I want to design a synchronous, let's be simple, 3-bit up counter. A quick review for all of you. How do I design a synchronous 3-bit up counter? A synchronous 3-bit up counter. Okay, so what is the truth table? I'll explain you very briefly what is the truth table. Q2, Q1, Q0, and since it is an up counter, it is going to go up. So initial state 0, 0, 0, next up 1, 2, 3, and etc, etc, etc. Okay. This is the count pattern. And back to 0, 0, 0. Back to 0, 0, 0. Now, let us actually make the transition table. Let us actually here make the transition table. The next state table. Okay, so transition table ke liye I need the current values. Since I'm using 3-bit, let us design using T flip-flop, or you can design even using the JK flip-flop. Okay, I have Q2, Q1, Q0. Then I have Q2 plus, Q1 plus, Q0 plus. As we know, these are the next state. Okay, so this is the next state. This is the transition. Let me write down here. This is what is the next state I'm writing for a corresponding given state. So what can be the corresponding given state? For 3 bits, I will write down all combination once again. These are all possible combinations of 3 bits. Okay, now if 0, 0, 0 is the current state, next state is 0, 0, 1. That is what is the up counter. So if 0, 0, 0, here I will write 0, 0, 1. If the current state is 0, 0, 1, next will be 0, 1, 0. 0, 1, 0 current hai, so next is 3, that is 0, 1, 1. Similarly, keep writing the next state for all of them. Just keep writing the next state for all of them. If the current state is 1, 1, 1, the next state will be 0. It will count. It will repeat. So after 1, 1, 1, the next state is 0, 0 and 0. 0, 0, 0. Now, let's say I'm designing using T flip-flop. What are the excitation signals? What are the excitation signals? That means excitation signals, yeah, excitation table means what should be the value on the T flip-flop you apply. What should be the value of the T flip-flop that you apply to get this state transition. Now T2 will be the input to the Q2 flip-flop, T1 will be the input to the Q1 flip-flop, and T0 will be input to the Q0 flip-flop. Correct? Right. Now see, look into the Q2 everybody. Everybody look into the Q2. 0 to 0. Now 0 to 0 means there is a same state, and for same state T input should be how much? For the same state T input should be 0. Now again same. Here comes a transition. Here comes a transition for the first time. Okay, the same means T0, T0. Now you get a transition. Q2 becomes 0 to 1. 0 to 1 means toggle. 0 to 1 means toggle, and toggle means T input should be 1. Toggle means T input should be 1, because we all know that whenever T is equal to 0, the state doesn't change, but when T is equal to 1, the next state toggles. Q bar. Q plus equal to Q bar. अब आ जाते हैं again 1 to 1 sir same, 1 to 1 same, 1 to 1 same. Last में toggles. Toggle means take the T input as 1. Okay, the same 0, 0, 0, and then toggle. This is the table. This is the table for T2. Now come here. Now come here for the T1. 0 to 0 same, 0 to 1 toggle. 1 to 1 same, 1 to 0 toggle. So alternately it is same and toggle. Alternatively it is same and toggle, same, toggle, same, toggle, same, toggle. Just keep checking. But when you go to the LSB, okay, 0 ka 1 hua, 1 ka 0, 0 ka 1, 1 ka 0, 0 ka 1, 1 ka 0. At every clock, at every transition, the Q naught, that is the LSB, always toggles. At every combination it toggles, and that means at all of these combinations T naught is fixed at 1. T naught is fixed at 1, right? T naught is fixed as 1. Some words are not okay. Prasiddha Rakesh, I will inform this to the concerned team dealing with the scholarship test. Okay. Yeah, you have to go for MTech, Mohammed. You have to go for MTech. चलो अब आ जाते हैं. So we are able to clearly see that the value of the T naught is equal to 1. That is concluded. Okay. What about the T1? Okay. T1 के लिए हम जाएंगे and T1, T naught तो 0, 1 है. T1 is high at 4 combinations. What are those 4 combinations? When the input, this will be taken as the input. This is the current state. This is the current state. We have to derive the T inputs as a function of current state. Okay. So ये हो गया. T1 is equal to summation of what minterms of the current state? कहाँ high है? 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1. Correct. Alternatively, it is high. So minterm 1, 3, 5, 7. Then I will simplify this. And T2 is equal to T2. अब T2 कहाँ पे high है? T2 is high at these two places. That is the minterm number 3, minterm number 7. Okay, that is summation of the minterm 3 and minterm 7. That is the minterm 3 and minterm 7. Okay, everybody? Now, what is the simplified form of this? What is the simplified form of this? I'll just feed to a 3 variable map. The 3 variable K map, the inputs being Q2, Q1 and Q0. K map, enough practice we have done in the first session. It is 1, 3, 5, 7. So this is 1, 3, 4, 5, 6, 7. Clearly there is a single group that is coming up. Clearly there is this single group coming up, and what is the value of that group? What is the value of that group? It is clearly lying inside Q0. It is clearly lying inside Q0. So this is equal to Q0. But if I draw the K map for the next one, for the T2, it is summation of the minterm 3 and 7. So this is 3 and this is 7. So there is a pair coming up, and that pair is Q1 and Q0. It is common to Q1, Q0. So this answer is equal to Q1, Q0. This answer is equal to the Q1, Q0. Now, what is the hardware? What is the logic circuitry? I have taken only a 3-bit case here. I'll generalize and tell you the 4th-bit case also. Okay. This is the input T0 starting from the LSB, output Q0. Input T1, output Q1, input is T2, output is Q2. Okay, the T0, as we have discussed, is always 1. But what is the value of T1? Everybody see, T1 is the Q0. T1 is the Q0. The value, the Q0, the current state goes to the T1. What is the T2? It is Q1, Q0. It is Q1, Q0. So Q1 is also required, has to be multiplied by Q0. So you have to feed both of them into this 2 input AND gate, and this goes to the T2. This goes to the T2. This goes to the T2. Since I have designed a synchronous counter, all of them will be fed with the common clock. All of them will be fed with the common clock. Then only it is known as the synchronous counter, and this is the hardware. This is the hardware of what is known as a 3-bit synchronous up counter. 3-bit synchronous up counter. No, Rakesh, it is general discussions of sequential circuit questions, okay? And we are specially not discussing PYQ. Maybe 1 or 2 PYQs we discuss in sequential. Rest all are the questions not PYQ, and we are going to go for MSQ question also. Okay, guys. So this is what is a 3-bit synchronous up counter. What is the hardware involved, and what is the speed of this circuit? What is the hardware and what is the speed of this circuit? Okay. Now, because all the flip-flops are fed by the common clock. All the flip-flops are fed by the common clock. So all of them will be active at the same time, and suppose all of them have the same propagation delay. Okay, all of them have the same propagation delay. Okay, मैं यहाँ पे बता देता हूँ. Let's take some extra slides. Let's say TPD is equal to propagation delay of each flip-flop, and we have assumed to be same. All flip-flops are identical. All flip-flops are identical. Propagation delay of each flip-flops is TPD, suppose. Okay, that is equal to the TPD. Acha, that is equal to TPD. So what is the total propagation delay? What is the propagation delay of the synchronous counter? What is the propagation delay? So TPD is the propagation delay of each flip-flop, but all the flip-flops are active at the same clock. Now suppose the clock positive edge comes, all flip-flops are ready, and if all flip-flops are ready, all will try to produce the output after TPD. So the entire output, all the three outputs, Q2, Q1, Q0 will be produced after TPD. There will be some delay of AND gate, but that is negligible in front of delay of flip-flop, so I am neglecting that AND gate delay here. So what is the total propagation delay of synchronous counter? That is also equal to TPD. Guys, that is also equal to the TPD. That will also be equal to TPD. So the total propagation delay of synchronous counter is equal to the delay of one flip-flop, right? Whether it is 1 bit or n bit, whether it is 2 bit, 3 bit, here we have discussed 3 bit. In general, it is n bit, does not matter, but the total propagation delay is equal to only TPD. Is equal to only TPD. Okay. And what is the total hardware? Guys, what is the total hardware? Now let me give you the hint. Yahan pe you have seen, because it is 3 flip-flops, because it is 3-bit counter, you have 3 flip-flops. Other than 3 flip-flops, you have one AND gate. What will happen next? Suppose you wanted to design a 4-bit up counter. Suppose you wanted to design a 4-bit up counter. I will tell you the answer, guys. I will tell you the answer. Chalo, yahan likh lete hain separately. Suppose you were designing a 4-bit up counter by the same method. 4-bit synchronous up counter by the same method, by the same method. Okay. Yes. So what is the answer going to be? What is the answer going to be? Please look. Same procedure we will follow. T0, T1, T2, T3. And if we follow the same procedure, guys, result T0 again 1. T1 again equal to Q0. This T1 again going to be equal to Q0. The T2 is again going to be equal to Q1, Q0. T3 extra aega na, 4th flip-flop will be there. 4th flip-flop will be there. Okay. And that is going to be nothing but Q2, Q1, Q0. Q2, Q1, Q0. It is going to be the AND of previous 3 outputs. It is going to be the AND of previous 3 output. Now, does it mean that does it mean that I need a 3-input gate? No. Dekho, this is already available. Q1, Q0. You will take another AND gate and feed it to the next flip-flop. Feed it to the T3, guys. Right? Feed it to the T3. Feed it to the T3. Right? Okay, feed it to the T3. Yes, it is visible ABD. If I solve 10 years, we can able to solve. Yes, 100%. But it will be better to target 15 at least ABD. Okay. Now come on, guys, come on, have a look into this one. Okay. So what is extra? 4-bit means 4 flip-flops, and in addition to that, one more extra AND gate, that again of 2 input. Because Q1, Q0 already you have designed. Q1, Q0 is designed. You only need to AND with the Q2. So only 2 input gates are extra. Only 2 input gates are extra. Okay, only 2 input gates are extra. That is what it is. So what is the total hardware? Total hardware for an n-bit counter will be n flip-flops. Plus n minus 2. For 3-bit you have 1 AND gate. For 4-bit you have 2 AND gates. So it is n minus 2 input AND gates. Right. But if I want to discuss about the ripple counter, sir, if I want to discuss about the ripple counter, have a look into this design. 3-bit ripple up counter. 3-bit ripple up counter. अगर हम इसको डिस्कस करें, if I want to discuss a 3-bit ripple up counter. If I want to discuss a 3-bit ripple up counter, okay, this is T0, T1, T2. Ripple counter means all the flip-flops, whether it is designed using T flip-flops or JK flip-flops, whatever it may be, all flip-flops in toggle mode. All flip-flops should be in the toggle mode, and the T flip-flop is in the toggle mode if its T input is 1. So here you don't have to worry about the T input. T input should be always 1 to design this ripple counter. All flip-flops should be in the toggle mode. Okay? Okay? All flip-flops should be in the toggle mode. Okay? The clock, here I am taking a negative edge triggered clock. The clock is only applied to the LSB flip-flop. The clock is only applied to the LSB flip-flop, and then the output of every flip-flop Q0 will be serving as the clock for the next flip-flop. Then the output of this flip-flop Q1 is going to serve as the clock for the next flip-flop, that is the T2. This is the T2. Okay. Okay. So output of every flip-flop will be acting or will be serving as a clock for the next higher order flip-flop. That is what is the consideration here. That is what is the consideration here. Okay. Chalo. Okay. This is what is a 3-bit ripple up counter. That is counting from 0, 1, 2, 3, 4, 5, 6, 7 back to 0. Now you have to remember some patterns. See, I will tell you one simple pattern, modify and remember everything. See, what is the type of clock connection here? There are n number of ways of remembering the trick. I will say simply that whenever the clock is of the connection Q output to the negative edge. Okay, so whenever you have Q output to the negative edge, if this is the clock connection given, then it is a up counter actually. Okay. Then it is the up counter actually. Okay? Q to negative edge, up counter. Just put this in mind, feed this in mind. Now what will happen if I take the connection from Q bar and I keep the device as negative edge triggered only? I am taking the connection from Q bar. So if any one variable is changed, up will become down. Okay. Suppose sir, I take from Q only, but I make positive edge. I don't remember second, third result. I only remember one. Q2 negative is up. So Q2 positive. Q2 positive. One connection change, the type changes to down. If it is Q bar to positive, just relate with respect to the first reference. Just relate with respect to the first reference. The first is Q to negative. This is Q bar and positive. Both change. So type will change 2 times, up to down, down to up, up to down, down to up. So it remains up only. There is no type change. Okay. So what is important for you is to remember this. Just remember this. Only one result. You don't have to remember the table. Only one result. You will be able to identify the type of the counter. Okay. Acha. Now next important point to note is, what is the total propagation delay of n-bit ripple counter? Yes, now if you are able to see, okay, here it's not the synchronous counter, it is going to be a ripple counter where the output of every flip-flop is going to be served as the clock of next. So where does the clock is applied? Actually, external clock is applied only to LSB. This will take a time of TPD. Same thing will assume every flip-flop has a time delay, propagation delay of TPD. Okay, TPD. This TPD, guys, in the case of flip-flop, let me mention here, TPD, in the case of flip-flop, what is TPD? TPD is actually defined as T clock Q. That is, what is the meaning of propagation delay of a flip-flop? The time between the arrival of clock edge and the output. Okay, this is the clock edge coming. after the clock edge comes, the flip-flop is active. After the flip-flop is active, after how much time the output comes? After how much time the output comes, that is known as the delay of the flip-flop. So TPD here is T clock to Q. Okay, so once again I will assume that the TPD, every flip-flop has the same TPD. Okay, so once, suppose TPD 10 nanoseconds hai, after 10 nanoseconds only the first flip-flop will be able to compute its output. And only after 10 nanoseconds we will be able to obtain the clock for the next, isn't it? Only after 10 nanoseconds we obtain the clock. So up to 10 nanoseconds this cannot operate. This is not synchronous. After 10 nanoseconds it starts computing and it again takes 10 nanoseconds. It again takes 10 nanoseconds. So this output is produced total after 20 nanoseconds. So up to 20 nanoseconds, this flip-flop is idle. It cannot perform. After 20 nanoseconds, it is getting its clock. It will again take 10 nanoseconds. So total 30 nanoseconds. This output will be obtained after 30 nanoseconds. So what is the total delay? It is 10, 10, 10. It is 10, 10, 10. In general, let me write down. What is the result in general, guys? In general, okay, the delay is given by n. Here it was 30, 10, 10, 10 3 times because it was 3 bit. If it is n bit, it is n times the propagation delay of a single flip-flop. So if more number of flip-flops, if higher bit of flip-flop you have to design, more will be the delay. So ripple counters are slow. Ripple counters are slow. Okay, but it requires, if it is slow, so there has to be some advantage also. Advantage is hardware. It requires less hardware. Less hardware means less money. You pay less, you get less speed. Very simple. Okay, so total hardware here is only n flip-flops. No additional logic circuitry. Only n flip-flops. Only n flip-flops. ठीक है. अच्छा. One more thing I will add on here in these slides only. यहाँ पे एक और चीज ऐड करेंगे. So please note that in the case of synchronous counter, the total propagation delay is TPD. Okay, so what is the minimum clock time period? What is the minimum clock period? That is also TPD. So what is the maximum clock frequency? There can be the questions on the maximum clock frequency. The maximum clock frequency is clock frequency is 1 upon time period. If time period is minimum, clock frequency will be maximum, and that is given by 1 upon TPD. Okay, 1 upon TPD. 1 upon TPD. The simple logic is, have a look into this. This is what is known as the clock period, na? The time between consecutive positive edge. Okay, at every positive edge we start computing next calculation. But what is the time required by the synchronous counter for one calculation? TPD. And when should be this calculation complete? This should be completed within 1 clock period. So the next clock edge should not come before the first calculation is over. So what is the minimum value of this clock period required? Very briefly I am telling you, but if you have any doubt, please ask me. What is the minimum value of the clock period required? Okay, it is the TPD. It is the TPD. ठीक है? चलो. Similarly, going ahead here, let me write down the results here as well. Very important results these are. So what is the minimum? What is the minimum T clock here? The minimum T clock here is equal to the total delay that is required by this ripple counter, that is NTPD. So what is the maximum clock frequency? What is the maximum clock frequency? 1 upon NTPD. 1 upon NTPD. Ripple is slower but requires less hardware. Synchronous is faster but it requires more hardware. Simple, it's a balance. Undoubtedly, it's a balance. Okay. Chalo. Thanks, Ankush. No, as of now for aerospace, there isn't any separate content, Krishnan. If there is, you will get the update. But as of now, I think there is no separate content for aerospace. Only some common subjects you can take the guidance. Subjects which may be related with mechanical or general subjects like maths and aptitude. Okay. So these are some important results. Now, because we have discussed this, we'll come back to this later. है ना? इस पे बाद में आते हैं. Let us actually go and discuss some concepts related to it. Let us go and discuss the concepts related to it. ये आ जाते हैं. Let me come to this MSQ question. Let me come to this MSQ question first. Synchronous construction reduces the delay time of a counter to the delay of single flip-flop and a gate. True or false? MSQ question, guys. Yes, that is what I just explained you. That is why I'm coming to this. A mod 10 counter is also known as a decade counter. This is a separate point, but yes, any mod 10 counter is known as a BCD counter, also known as a decade counter, because it counts one decade. One decade is equal to a factor of 10. So this stands out to be true. Asynchronous decade counter increases its value by 10 for each clock pulse. Whether it is asynchronous or synchronous decade counter. Asynchronous or synchronous decade counter. A decade counter will have a total number of states equal to 10, but it will not increase the value by 10. At every clock pulse, it will keep increasing by 1, 1, 1. It will count 0, then 1, then 2, etc. up to 9 and then back to 0. So it will increase the value by 1 only. The total values will be 10. So this is false. This is false, okay? This is false. The modulus of a counter is same as the maximum count. Tell me, what do you know about the modulus of a counter? The modulus of a counter, is it same as its maximum count? No. The modulus means the total number of states. I am going to take a question today probably where, yes, we are going to take a question where you are going to see count sequence. Suppose there can be a counter. Let's not talk about the question. There can be a counter counting 2, 3, 6, 7. There can be a counter counting 2, 3, 6, 7. Or you can design an odd number counter. You can design an odd number counter counting 1, 3, 5, 7. Counting 1, 3, 5, 7. Total number of states 4. Mod number is 4. But the maximum value 7. So mod number is not 7. Nah? So what is the mod number? What is the modulus? It is the total number of states. It is not related with the maximum value. So ye bhi false hai. So what is my correct answer? Is option number AB for this multiple select question. For this multiple select question. Okay? Chalo. Multiple select question. Before showing you the next question, let me keep mixing the question here. Let me take two simple questions here. Little bit mixing I am doing for the questions here. A cascade of 3 identical modulo 5 counters has an overall modulus. A cascade of 3 identical modulo 5 counter. Whether it is identical modulo 5 or even unidentical counters, whenever counters are cascaded, okay, for cascade combinations, what is the mod numbers? For any cascade connection of counters, mod numbers are what? Mod numbers are multiplied. So what is going to be my answer for the question? All are mod 5. So 5 into 5 into 5, that is equal to 125. 5 into 5 into 5 is 125. So the answer for this numerical answer type question is 125. Let's not prove this. Let's focus on questions now. Whatever important part I am discussing related theory, but this is okay, easy. So whenever counters are cascaded, the mod numbers is multiplied. The mod number is multiplied. Okay. Okay. Now answer me this question. Some simple concepts we are relating. Okay. So I am doing a mixing of questions as in what we are discussing. A counter is designed with 6 stages of the flip-flop. A counter is designed with the 6 stages of the flip-flops. Okay, everybody? Determine the output frequency at the last stage. Last stage bole to MSB stage. When the input frequency is 1 megahertz. Now, if the counter has 6 stages, what is the mod number? It is given by 2 raised to the power 6. Okay. Now, the concept to be used here, the result to be used here is the frequency at MSB, guys. The frequency at MSB is clock frequency or input frequency divided by the mod number. So, what is going to be the answer here? The answer is the clock frequency, which is 1 megahertz, divided by the mod number, that is 2 power 6. But we need the answer in the form of kilohertz. Right? So that is 1 megahertz is 1000 kilohertz divided by 2 power 6, that is 64. 1000 divided by 64, quickly. Divide by 64, the result is 15.625. 15.625 kilohertz. 15.625 kilohertz, right? Correct. Option number C. Acha, there can be even a general picture. There can be a more generalized picture of this. What is the more generalized picture? मैं वो भी बता देता हूँ आपको. Since we are discussing, let us discuss every particular possibility. Let us discuss every particular possibility here. Suppose this is LSB, right? So this will going to be Q naught, right? This is the MSB. This is going to be the Q n minus 1. Okay, because we are talking about the n-bit design. We are talking about the n-bit design. So this is going to be Q n minus 2. This is going to be Q n minus 3. Even let me take one case here as well. So after the LSB, this is going to be the flip-flop having Q1. Okay, so what is going to be the clock frequency? I am not including any more hardware. It may be a ripple design, it may be a synchronous design, whatever it could be. So what is the frequency here, guys? That is what I just told you. What is the frequency at the MSB? It is given by the clock frequency. Okay. So you apply some clock of a specified frequency divided by 2 raised to the power n. Okay, let's say it is a n bit up or a down counter. It may be ripple or it may be synchronous, anything. Let's say it is a n bit up counter. So f clock divided by 2 power n. What about the frequency here? What about the frequency here? It is f clock. Now you have to see, guys, very simple logic is, that was the LSB, this is the MSB. So from LSB to LSB, how many flip-flops? How many bits? N bits. Now total n bit design you have considered. So forget, now discard this one. Till this point, how many flip-flops and how many bits are used? Till this point, n minus flip-flops. If I exclude the MSB, till this point, n minus 1 flip-flops are used now. So your answer will be, simply remember like this. Your answer is going to be f clock divided by 2 ki power n minus 1. 2 raised to the power number of flip-flops. What is going to be the frequency here? This is going to be clock frequency divided by 2 ki power n minus 2. Okay. Similarly, what is going to be the frequency here? Just at the second one. So only 2 flip-flops are consumed up to this. So it is going to be 2 power 2. What is the frequency obtained at the LSB? That is going to be the clock frequency divided by 2. That is going to be the clock frequency divided by 2. That is only 1 flip-flop, the 2 power 1. So this is the general picture, and the previous one is also the question based on that. The previous one is also a question based on that. Okay? Chalo. Now, basis of this, where shall I move? Now let me move towards questions. Pehle isse related finish karte hain. Let's finish the questions related to this. Come here, this one. Okay. One of the MSQ question we have discussed. The next MSQ question. Okay. Now passwords is already available in that particular class. So for passwords, you have to stay updated to the class. That's a simple rule here. Okay. So an input clock frequency of 60 megahertz is given to a cascade combination of mod 5 and mod 15 counter. Output frequency will be 3. Is it correct? Is it correct? Dekho, option number A, output frequency, they are asking. Output frequency, MSB frequency, is known as the clock frequency divided by n. Okay, now what is the clock frequency? 60 megahertz. 60 megahertz. That is divided by mod number. What is the mod number? There is a cascade combination of mod 5 and mod 15. Mod 5 and mod 15 cascaded hai, so the mod number is multiplied actually. Is it equal to 3 megahertz? They have added 5 and 15 and 60 by 20 will be 3, but we don't add, no, it's multiplied. So this is, whatever the result may be, this is not 3 megahertz. It's actually, kitna hua? Cancelled 4. This is 0.8 megahertz actually. So this is wrong. It is not 3 megahertz. The minimum clock frequency that is to be used for an n-state ripple counter is given by, already I explained you this one, correct. This is what I already explained you, na? This we have discussed fully. Okay. Okay. The propagation delay of the flip-flop in a ripple counter does not impose a limit on the frequency at which the counter... Array. Achha, sorry. ये मिनिमम क्लॉक फ्रीक्वेंसी लिख दिया, सो दिस इज रॉन्ग. ओके, दिस इज द फॉर्मूला फॉर मैक्सिमम क्लॉक फ्रीक्वेंसी. ये जो फॉर्मूला है ना, मिनिमम टाइम पीरियड एंड मैक्सिमम क्लॉक फ्रीक्वेंसी, दिस इज द फॉर्मूला फॉर guys maximum clock frequency. So B is wrong. B is also wrong. We have to be very specific about the words. Okay, propagation delay of flip-flop in ripple. What is the propagation delay? The propagation delay of the flip-flop in a ripple counter does not impose a limit on the frequency at which the counter can be approached. Clocked. अरे how the frequency that it can be clocked, इसी से देख लेते हैं, and that is given by 1 upon n TPD, where TPD is the propagation delay of the flip-flop. TPD is the propagation delay of flip-flop, so this is also wrong. Okay, last one. In a 4-stage ripple counter, the propagation delay of each flip-flop is 30. What is the maximum frequency? Is 8.33 megahertz, for which it will work reliably. Okay, option number D calculate करेंगे. The maximum clock frequency for the ripple counter. The maximum clock frequency for the ripple counter is given by 1 upon n TPD for a ripple counter. They are talking about 4-stage and TPD is 30 nanoseconds. So this becomes 10 raised to the power 9 divided by 120, or they are asking in megahertz. So 10 raised to the power 3 into 10 power 6 upon 120. 1000 divided by 120. Yes, 8 is going to come. Yes, this is 8.33 into 10 power 6, which is megahertz. So this is 8.33 megahertz. This is known as the 8.33 megahertz. Correct. Yes, this is okay. Option number D is correct. So yes, as I explained you in the last class also, dear students, as I explained you in the last class also, MSQ IIT has specified about MSQ that one or more than one can be correct. One or more than one option can be correct. Matlab one can also be correct, na? That is also a category of MSQ. So don't be surprised, don't be shocked, and don't be confused. Yes, this is a MSQ where only one option is correct. Where only one option is correct. Where only one option is correct. Okay? Where only one option is correct. Only one. Okay? Next MSQ question here. For a divide by 83 ripple counter, we need 7 flip-flops. We need 7 flip-flops. If it is 6 flip-flops, na, 6 flip-flops can produce 2 power 6 equal to 64 states maximum. Right? So any number of states greater than 64, you need 7 flip-flops. Any number of states greater than 64, you need 7 flip-flops. So that is totally correct. Okay. Up to 128 states, you need 7 flip-flops. That is very correct. Okay. Now divide by 83 का मतलब है the mod number is equal to 83, and for 83, yes, 7 flip-flops are required. Correct. So this is true. Option number A. A decade counter can be constructed by cascading a mod 5 and mod 2 counter. Yes, because when you cascade 2 counters, the mod numbers are multiplied, so 5 2s are 10. Yes, so that will become a mod 10 counter, and any mod 10 counter is a decade counter. Okay, it counts a particular decade. Okay. A 3-bit synchronous down counter can be converted into a 3-bit synchronous up counter. Very interesting. Tell me yes or no. A 3-bit down counter can be converted into a 3-bit up counter. Down to be converted to up. Chalo. A down counter, can it be converted to up, or vice versa? If it is true, it has to be true both sides. If it is true, it has to be true both sides. This is okay. Dekho, down means I start 111, 110, 101, 100, 0113, then 2, then 1, then 0. Up means 000, 001, 010, 011, 100, 101, 110, 111. Is it possible or not? Dekho, the only difference is 111 is 000, 110, 001. 101, 010. So all Qs are complemented of each other. Can I say like that? Can I say like that? All Qs are complemented. Whether you see from down to up or up to down, all the Q are complemented. Okay. Pick up any Q. If this is 0, here it is 1. Next. Sir, if this is 1, here it is 0. Take up any particular Q, corresponding Q, it is appearing as complemented. It is appearing as complemented. So what you have to do now, If I take you back towards the design of up counter, let me go back where we have discussed the up counter. Have a look into this design. Okay, see, a very simple change is from Q, rather than Q naught, if you take Q naught bar and feed here, similarly Q1 bar you feed here, ye bhi Q naught bar se aayega. So whatever Qs you were using in designing the hardware, use it as Q bar, it will automatically become down counter. You can check in detail, but the logic, the truth table says that whatever Q, rather than Q naught, wherever Q naught is going, don't use Q naught, take the Q naught bar. And in the flip-flop, both the outputs are available, Q and Q bar. Okay. So you just have to change the connection. You don't have to implement extra hardware. You just have to change some wire connections, right? Rather than Q1, you have to take from Q1 bar. This particular up counter will be going to behave as a down counter. Okay. So yes, this is true. This is true. A synchronous decade counter cannot be constructed by using flip-flops. Yeah, why not? It can be constructed. Ye to false hai. Okay, so the correct answer is option number A, B and C also correct. A, B, C is correct, D is wrong. A synchronous decade counter can be constructed. How it can be constructed? Like I have given you the design of up counter. Like I have given you the design of up counter. Similarly, the same method, take the current state, take the next state, take the excitation signal and design the counter. Only thing is, last state is, agar decade counter bana rahe ho, to 1001 4-bit you will use. After 1001, after 9 you have to make 0000. You don't have to take 1010. 0 to 9. Total 10 values if you want, that is 0 to 9. You can design, yes. They are not asking the design, whether it is possible. Yes, it is possible. And if you have studied the digital circuits full in detail in theory, you must have seen that design. Okay, the answer is yes, it can be designed. They say cannot be constructed, wrong. So correct answer for this MSQ question is A, B, C. The correct answer for this MSQ question, guys, is A, B, C. चलो अब किस question की तरफ आपको ले जाएं? What is the next question? I'll take you towards this particular question. Have a look into this question. The frequency of the pulse Z, seen at the last, is how much? So 10-bit ring counter, what is the mod number? For a 10-bit ring counter, what is the mod number? What is the mod number of a ring counter, guys? It is equal to n. Okay. Parallel counter, just like synchronous counter, if it is 4-bit, the number of states is 2 power 4. 2 power 4. Okay. Ripple counter, already they have mentioned mod number. They have not mentioned bit. So mod number 25 means we only need the mod number, na? That is 25. And for Johnson counter, the number of states is double the number of bits. N-bit ring counter, mod number is n. N-bit Johnson counter, mod number is 2n. Mod number is 2n. So what is the total mod number? All of these are connected in cascade. What is the total mod number? N1, N2, N3, N4. That is 10 is multiplied by 2 power 4, which is 16, is multiplied by 25, is multiplied by lastly 8. Okay, so let us see how much is the final result. Yes, this is 32,000. So the total mod number of this counter is 32,000, and then the frequency at Z is the input frequency, that is 160 Hertz divided by 32,000. 160 Hertz. Now that is in Hertz, sorry. So this is a misprint, guys. This has to be 160 kilohertz. Take this as 160 kilohertz. It's a typo error. Okay, 160 kilohertz. Let me write down 160 kilohertz. Okay, so kilo will cancel with the 1000. So that becomes 160 divided by 32. Answer will be 5. Answer will be 5 Hertz. Okay. Answer is going to be 5 Hertz. Make this as 160 kilohertz. Okay. That can be 160 Hertz also, but change kar diya. Otherwise, this can become 0.005. That is also okay. But take that as 160 kilohertz. That is okay. Okay, guys. Okay. So answer is 5. This one again a simple one. This was again a simple one. Now let me take you towards the next variety. Lots of variety of questions are there ready for us. चलो अब थोड़ा सा counter का count कर लेते हैं. We have seen some important conceptual questions related here. Now let us go to this question. Let us count this count sequence now. Let us count the count sequence now. Yes, Pradeep. Yes, you can. Third year students can write down. Okay, come to this one. What is the modulus of the following counter? What is the modulus? How many states? Modulus means number of states of this counter. Have a look into this and let us start. We all know the JK flip-flop input combinations. What is the next state of JK flip-flop? So let me just keep writing here. Okay, let us start with the Q2, then Q1, and then Q0. The funda is always start with 0, 0, 0. Always start with the reset state. Okay, now see the next state. Let us start with the Q0. Okay, so what is the input to the Q0? Where is the J0? J0 is K2 bar, Q2 bar, and K0 is coming to be Q1. Okay. अच्छा, यहाँ पे एक चीज आपको देखने लायक है. When both the JK inputs are toggle of each other. Please remember, when both the JK inputs are toggle. See, this is Q0, so this is Q0 bar. Here you get Q1, so here you get Q1 bar. JK are toggle of each other, so it behaves as what? Just have a look into this picture. Just have a look into this particular picture, everybody. This is J, K, Q, Q bar, and suppose you apply X here and you apply X complement to the K. That is what is happening in the last two flip-flops. Dekho. Okay, last two flip-flops. So dekho. What is the next state equation? What is the next state equation of JK flip-flop? It is given by the formula JQ bar plus K bar Q. Hope you remember. The next state equation of the JK flip-flop is JQ bar plus K bar Q. Now, what is there on the J? It is X. So XQ bar plus K bar. So what is there on the K? K is getting X bar. So X bar bar. X bar bar will be X, and X is common. You get Q plus Q. Q bar plus Q is equal to 1. So you get only X. So what is the Q plus? It is only equal to X, and it is behaving like what flip-flop now? It is behaving like what flip-flop? I already replied to you, Pradeep. Please do not spam the comment box. What is the value of Q plus is equal to X? So this is like what flip-flop? It is like a D flip-flop, isn't it? This is like a D flip-flop. This one is like a D flip-flop. In short. Okay, Q plus equal to D. Name में क्या रखा है? Let's say this is named as D. So Q plus equal to D. Okay, so when both the inputs of JK are toggled, it behaves as a D flip-flop. It behaves as a D flip-flop. ठीक है? Correct है? It behaves as a D flip-flop. Got it. चलो, cool. Okay, so now let's come here. If it is D flip-flop, what is going to happen? Q1 plus is equal to what is available on the input is Q0. Similarly, Q2 plus will be equal to what is available on the input is equal to Q1. What is available on the input? Okay, so हमें इतना बोलना है, whatever is the current value of Q0, guys, will be the next state of Q1. Whatever is the current value of Q0 will be the next state of Q1. Whatever is the current value of Q1 will be the next state of Q2. Whatever is the current value of Q1 will be the next state of Q2. So these two you can just simply left shift. Okay, you can simply left shift. These two you can simply left shift. Now come to the Q0. Okay, to Q0, to see the value of Q0, I need to see what is J0, K0. तो देखो J0 कितना आया है? Q2 bar, and this is Q1. देखो, please see very carefully. What is the value of Q2 right now? Right now, this is the current state. Okay, this is the upcoming state. This is appeared. This is appeared only in your copy, only in my board. It is a synchronous design. Every transition 1, 2, 3 will occur at the same time. Okay, not individually. So what is your current state? This is your current state. So currently Q2 0 hai. So the 0 bar is 1 here, and Q1 is 0. So Q1 is 0. So what is the current combination, guys? J1 and K0. What is the current combination? J1 and K0. J1 and K0, the device is set. The device is set. So Q0 is set. Q0 set hai. Chalo. Now next. What is the next thing you have to do, guys? Next thing is, this is just left shifting. इसको left shift किया, इसको left shift किया. Only take the LSB case. Now LSB के लिए I need to again see the connection. So what is the value of Q1 now? What is the value of Q2 now? Q2 is again 0, 0 complement 1. What is the value of Q1? Q1 is also 0. Again same 1, 0. Again same 1, 0. J1 K0. J1 K0. Arre sorry. ये 1 slide किया ना. J1 and K0. It is again set combination. So this remains to be set. This remains to be set. Now again shift. Again first shift. This is 1. this is 1. What comes here at the LSB? ये देखने वाली बात है. So once again, now what is the value of Q2, guys? What is the value of Q2? What should be the value of Q2 now? All going correct? Yes. तो Q2 अभी कितना है? ऊपर वाला वैल्यू देखना है. That is 0. तो 0 complement is again 1. Q1 is now 1. J1 K1 is toggle now. J1 K1 toggle, and toggle means this 1 will be complemented to 0. You get the next state. Okay. Now what is the value of Q2? Q2 is 1, so its toggle is 0. What is the value of Q1? Q1 is 1. So J0 K1 reset. J0 K1 reset. This is reset and rest is shifting. You get 100. You get a new state. 100. You get a new state. Now next again, what is the value of Q2? Q2 is equal to 1, so its complement is 0. Q1 is equal to 0. Guys, J0 K0, same state. J0 K0, LSB remains same. Rest, it is the left shifting. You again come back to the initial state 0, 0, 0. So what is the count sequence and what is the mod number? After solving it completely, I will write down the count sequence also. The count sequence Q2, Q1, Q0 is actually, where is it? 0, 0, 0, 0, 0, 1, 0, 1, 1, 1, 1, 0, 1, 0, 0, and 0, 0, 0. That is back. Okay, so it is back to 0, 0. What is the mod number? 1, 2, 3, 4, 5. How many states? 0, 0, 0 the repeat hai na? This is repeated. So what is the mod number actually? So mod number 1, 2, 3, 4, 5. It is a mod 5 counter. Mod number of the counter is 5. These can be definitely 2 marker questions, good questions in the gate. Okay, this is a mod 5 counter. Everybody, this one is a mod 5 counter. Got this one? Chalo. This is a mod 5 counter. Okay, and if you are all able, if you have done this one and if you have got this concept, a similar question again based on synchronous counter design, this is your homework number 2 for the day. Homework number first I have given you in the beginning only. This is the homework number 2 for tonight. This is the homework number 2 for tonight. Let's go to the next question then. Please solve the homework and comment your answer in the comment box. I will reply like for the previous classes. I have replied your answers in the comment box. Solve and comment in the comment box. Moving ahead. Okay, next question. The circuit shown consists of JK flip-flops, each with the active low asynchronous reset input. The counter corresponding to this circuit is what? The counter corresponding to this circuit is what? The circuit shown consists of JK flip-flops, we each with the active low asynchronous reset input. What is the counter corresponding to this circuit? What is the counter corresponding to this circuit? First of all, active low asynchronous reset pin. Okay, वो भी explain करेंगे. But what is the type of flip-flop? It is a ripple counter. The clock, the output of every flip-flop goes to the next flip-flop. So definitely it is a ripple counter. It is यहाँ पे है क्या नहीं? It is a ripple counter. But what type of ripple counter? The connection is Q to negative edge. The connection is Q to negative edge. When the connection is Q to negative edge, what type of counter you expect? Up. This is the only one fact you are remembering. Q to negative edge up. Rest you can derive. Rest you can just modify yourself. So Q to negative edge, it is a up counter. Achha. So definitely it is not a down counter. ये तो हटा देते हैं. It is not a down counter. But whether it is modulo 5, modulo 6, so what is the mod? See, if there was no reset, then it is a mod 8 counter. 3-bit, na? 3-bit can produce 2 power 3, 8 states. So it has to be modulo 8 counter if there was no reset, but there is a reset also given. Okay, active low asynchronous reset. Active low, what is the intent of this active low? यहाँ पे बोला है active low. Okay, so flip-flops, okay, will, अच्छा, asynchronous भी है. Flip-flops will immediately reset. Because it is asynchronous, it will not wait for the next clock. Flip-flops will immediately reset if suppose the reset pin, I call it as X, if X is equal to 0, yes, it will be active when it is receiving the low signal. It will be active if it is receiving the low signal. Okay, so let's suppose the reset input is X, and that is what is the symbolic representation of active low. Either they place a R bar, or they place a bubble, or they place both. To represent active low device, they place a bar or a bubble, or they can place both. So this is the graphical representation of that as well. So if X is equal to 0, flip-flops will immediately reset, guys. If the X is equal to 0, flip-flops will immediately reset. Flip-flops will immediately reset. Okay? Flip-flops will immediately reset. Chalo. Okay, so now what is X? Now what is this X? X means the output of this NAND gate. Okay, output of the NAND gate. X means Q2, and what is this? What is this? This is Q0. Correct. So Q0, Q1 bar equal to 0. X equal to 0 means the output of NAND gate is 0 if both the inputs are 1. Or I can say Q2, Q1 is 1 and both Q2, Q0 should be 1. Q2, Q0, sorry. So this is possible if both Q2 and Q0 are equal to 1. Then only X is equal to 0. So I say whenever the MSB, LSB, Q2, Q0 are both 1, the X will be 0. So now look at the count pattern. Now look at the count pattern. Q2, Q1, Q0. We have Q2, Q1, Q0. It's a up counter we have identified, and up counter hai, so we start with 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and etc, etc, etc. Okay, but what is the status of X? ये भी लिख देते हैं. Right, X is equal to 1 if and only if Q2 and Q0 are 1 at the same time. Okay, so Q2, Q0 are not both equal to 1. 1, 0, 0. Q2 is 1, but Q0 is low. 1, 0, 1. Look at this. At 1, 0, 1, Q2 and Q1 are both 1. So here X will be 1. Here X will be 0. Not 1, I'm sorry. X ko 0 hi humne dekha tha. X is equal to 0. Rest all X is equal to 1, and it is an active low pin. Now, as soon as X becomes 0, all flip-flops will now reset. All flip-flops immediately reset without waiting for next clock. Without waiting for the next clock. Okay. Okay. So, what is the next state? Next state is immediately 0, 0, 0. Right. So, this will no longer exist. And it will be transitioned to the next state of 0, 0, 0. That is repeated. Guys, this state should not be counted because all flip-flops immediately reset without waiting for the next clock. Immediately means without waiting for next clock. That is what is the meaning of asynchronous pin. Otherwise, if I say synchronous reset pin, so synchronous means what? Synchronous means synchronized with the clock. So it will work with clock. Asynchronous will work immediately without waiting for the clock. So this is a state which comes. But for a very minute amount of time, for a very small amount of time, it will not be active for one clock cycle. What is known as a valid state in the sequential circuit, in any circuit. A valid state is one which remains active for one clock pulse. Which remains active for one clock pulse. Which remains active for the one clock pulse. So it is not active for the one clock pulse, okay? It is not totally active for the one clock pulse. So this is not a valid state. So what is the mod number? Mod n is equal to 1, 2, 3, 4, 5. You are not going to count this. You are not going to count this. Yes, that is where many students commit mistake here. 5 or 6. It is 5. Okay, the state which will produce the reset combination will not be counted. But if the question is, okay, if the question is something like if reset pin is also synchronous, if the reset pin is also synchronous, then what will be the answer? See, if nothing is mentioned in the question, then by default you will consider asynchronous. Ye bhi jaan lijiye. If nothing is mentioned, you will by default consider asynchronous. Here they have mentioned asynchronous. They can mention synchronous to make a question. And if it is synchronous mentioned, then the answer will be, then what will happen? X equal to 0. All flip-flops will reset, but not immediately. All flip-flops will reset at the next clock edge. at the next clock edge. That means this state will remain in front of you. This state will remain for one clock cycle, and hence it is also a valid state, and hence it can be counted. And because it has to be counted, the counter will become mod 6 now. बहुत ही बढ़िया. The counter will become mod 6. The answer will be a 1, and that is where you make the mistake. Okay. So if it is asynchronous, it is mod 5. If it was synchronous, then it would be mod 6. Then it would be the mod 6, everybody. So correct answer is option number A here. The very correct answer is option number A. Everybody, correct answer is option number A. If I change the question to asynchronous, then it becomes mod 6 up. Okay, up and down already we have learned to identify. ठीक है जी. This question already solved. Now this question, the next homework for you. This is the homework number 3 for tonight. Homework number 3 for today. Okay. Because this is a combination of two things. One, it is again a ripple counter. That too, again, this is the LSB. See, how to identify LSB? In ripple counter, the clock is applied to LSB. So this is my LSB. Okay. And Q to negative H, Q to negative H. So it's a up counter. It's a ripple up counter. It is a ripple up counter. Okay. So the clock frequency here is how much? The clock frequency here is the frequency at Q3, that is the MSB. Q3 bole to MSB. What is the frequency at MSB? Clock frequency divided by mod number. Clock frequency to 1 kilohertz given hai. So you have to work on mod number. Like previous case you got mod 5. Divide by 5. Here whatever is the mod number, okay, again you will write down the entire state and you will see that, let's suppose reset is X. Okay, from where is the X coming up? Okay, from where is the X coming up? It is Q1 and Q3. And now even if I give 30 more seconds, answer will be done. So better you complete this as homework. Q1, Q3, correct? Q1 se aaya or Q3 se aaya? Okay, so you have to again work out, correct? So what is the mod number? You work out and accordingly, you will get your answer. Simple one. So this is the homework number 3 for tonight, guys. This one is your homework number 3 for tonight. Rest all these MSQs question ye dekh lena. These were good MSQs. Good means the concepts were very good here. So please go through these MSQs. Okay, now let me take up time hai abhi. Chalo, let's take one interesting question here. Let's take one interesting question here. Isko zarur dekhte hain. Yeah, here it is. Chalo. A good question. Some random flip-flop. Preset is not used, na? It's just given, but they haven't used it. Preset means if they use the preset, it is opposite of reset. Okay, the flip-flop will become set. The flip-flop will be equal to 1. Okay, when that pin is arrived. Okay, Sai Charan? Chalo. It's a random flip-flop, some MN flip-flop. An MN flip-flop works as follows. An MN flip-flop works as follows. If it is 0, 0, if the MN is 0, 0, next state will be 0. For MN 0, 1, the state remains same. For 1, 0, toggle state. For 1, 1, next state is 1. Next state is 1. So you have all 4 combinations given. Next state 0, this is known as reset. Next state same, it knows next state remains same. Complemented, this is toggle state. And 1 means set combination. What is the characteristic equation of such a flip-flop? What is the characteristic equation of such a flip-flop? So let's look into this. Let us look into this. Okay, let us look into this. Okay, so let's write down actually all 3 combinations. The current state, the inputs MN, and the next state. Okay, let us write down first the 8 combinations of these 3 bits. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. But now highlight whenever MN is 0, 0, the next state will be 0. Whenever MN is 0, 0, next state will be totally 0. Reset kar dena yahan pe. So this is reset and this is reset. Okay, everybody. Now, when the next state is 0, when the MN is 0, 1, what is the combination? 0, 1 pe next state remains to be same. Same. So if it is 0, remains 0. If it is 1, remains 1. Okay, so 0 here and 1 here. For MN 1, 1, for MN 1, 0, you have to toggle 1, 0 and 1, 0. Toggle means 0 ka 1 aega and 1 ka 0 aega. Okay, so let me write down this one neatly again. This is 0 complement 1, 1 ka complement 0, and last, when Mn is 1 1, the next state is 1. When Mn is 1 1, the next state is 1. So 0, whatever is the current state does not matter, next state is 1. So I can now say that, everybody, I can now say that the Q plus is high at the minterm 2, 3, 5, 7, feeding this to the K map, guys. Feeding this to the K map. What is the Boolean function? We need the next state expression, okay, of a randomly given flip-flop. So these can also be some good questions expected. Okay, so 1, 2, 3, 4, 5, 6, 7. So clearly there are two pairs coming up, two horizontal pairs coming up. This is Q bar M clearly, and this is Q, and within N. So the next state of this flip-flop is MQ bar plus NQ. MQ bar plus NQ. MQ bar plus NQ. Option number B ready, sir. MQ bar plus NQ. So randomly designed flip-flop you should be able to handle. You should be able to handle. Okay. Now, based on this, one more question. ये तो हो गया. This is again a good question, but still regular. Now, a randomly given flip-flop, and onto which a counter design. Onto which a counter design. Same data is given. Now, if I take a counter designed using this Mn flip-flops, what is the count sequence of the counter? And the interesting thing here is, it is again a ripple counter, but it's a asynchronous counter. I will not call it as a ripple counter. Okay, because all flip-flops are not in the toggle mode. If it were all flip-flops in toggle mode, why not toggle mode? What is the toggle combination? 1 0. So ye to 1 0 hai, this is 1 0, but this is not 1 0. If all flip-flops were in the toggle mode, and then you have Q2 positive edge connection, I will directly say it is a down counter. But last flip-flop ne condition change kar diya. Now remember, suppose if the question was 1 0 here, then all flip-flops are in toggle mode. 1 0 means toggle, and the answer is down counter. So count sequence is 7 6 5 4 3 2 1 0. 7 6 5 4 3 2 1 0. Okay, if this was 0. But abhi to nahi hai na, so let's solve it. Hope you have got this concept. So what is going to be this particular answer? Ye dekh lete hain. What is going to be this particular answer? Ye dekh lete hain. Come to this point. Okay, so 1 0 is toggle, 1 0 is toggle, 1 1 1 1 1 1. The next state will be 1. So again I will write down the count sequence. Have a look into this. We'll have to write down the count sequence. Q2, Q1, Q0, everybody. Okay, this is LSB, very clearly mentioned. Okay, so dekho, let us start with the LSB. 1 0. This Q0 plus is always equal to Q0 bar, because this is the toggle input. 1 0 means toggle. Similarly, this is Q1 plus, this is always going to be Q1 bar. This is also going to toggle, but when the clock arrives. Okay, और ये क्या है? Q2 plus, and 1 1 says it is next state is 1. So Q2 plus is always 1 if the clock arrives. But where is the clock? Clock is only applied to LSB. Rest you have to see. All are positive edge triggered. So LSB is always toggled. Q plus equal to Q0. Q plus equal to Q0. This is always toggle because clock is directly coming to here. So look into this. Okay, let us start with the automatically reset state. Now this is toggled. Now listen to this. Listen to this. If Q0 is toggled, this is a positive edge because the same Q0 is acting as a clock for the next flip-flop. And next flip-flop is also positive edge. So you have to wait for the positive edge on the Q0. And yes, positive edge on Q0 comes. So Q1 will also toggle. Bhai dekho na, Q1 is also ready to be toggled. Okay. Now, since Q1 toggled, this is also a positive edge. See, the Q1 is going as the clock. This Q1 is going as the clock for next flip-flop. So when you get the positive edge on Q1, the next flip-flop will be active and the next flip-flop, next state will be always 1. Whenever it is X state active, Q2 plus is 1. So yahan pe aa gaya 1. Now, whenever the LSB, whenever the external clock comes, ye to aata rahega na, you apply a periodic clock waveform. So this will again toggle. If this toggles, it becomes 0, and 1 to 0, 1 to 0 is a negative edge. So 1 to 0 is a negative edge. This flip-flop is not active. It remains in the same state. 1 to 1, there is no transition. So the next flip-flop is also not active. Ripple, it's a asynchronous design, na? If you get positive edge on one flip-flop, then only the next flip-flop is active. Chalo. Again, clock the periodic waveform, you apply after again some time, the positive edge will keep coming, and when the positive edge comes, this is going to be toggled to 0 ka 1. This is again positive edge. So this will toggle now 1 to 0. But 1 to 0 is a negative edge. So this will not be active. So it remains still in the same state. Next, again after certain time, next clock edge comes. So this toggles. But this is 1 to 0 negative edge. So ye does not change. This is 0 to 0, no transition. So next flip-flop does not change. Again after certain time, next edge comes. 0 to 1, positive edge, so this will toggle. This is again positive edge, so this remains to be set. But 1 1 1 now repeats. 1 1 1 now repeats. Okay, so what is, if repetition occurred, what is the count sequence? I can say 7 6 5 4 and then repeat. So what is the count sequence? 7 6 5 4, option number B. Beautifully designed question. Option number B, 7 6 5 4. The correct answer is option number B, that is the 7654. That is the 7654. Everybody, 7654 is the correct answer. Okay. What is the mod number? I told you the mod number is 4. Maximum count is 7. So what is mod number? Mod number is total number of states. In one question we checked, now mod number is not equal to the highest count. Mod number is number of states. Mod number 4, highest count can be anything. It's a good question. Randomly given flip-flop, and based on that one designed counter, okay, that too in the asynchronous mode, you have to solve it up. Okay. Chalo. Okay guys, so here it is. The last question as a homework for you. This is the homework number 4 for tonight. What is the value of register form from D flip-flop using Q0, Q1, Q2 as the output after 14 cycles? Okay, the hint is, if you have studied well enough, the output, the Q bar of the last one is fed to the D input of the first one. That is a Johnson switch tail ring counter, Johnson counter. If you take the connection from Q, it becomes a ring counter. It is a connection from Q bar, so it is a Johnson counter. So now the question can be solved very simply. How you can solve simply? What is the count sequence of Johnson counter? There is trick to remember it. You have to think about this and then comment the answer in the comment box. This is the homework number 4 for today. And guys, that's it for the session. The time is already 1:44. Okay, and lots of questions we tried to discuss. It was one session, around 1 hour 15 minutes we planned the session, but it went on for a long time, but no problem. Sequential circuits is, where even many more questions can be framed. Okay. But as promised, overall technical, more than 500 questions you will get in the champion series. Now guys, my next topic will be, listen to this very carefully. My next topic is going to be, what is that? Number systems. But it is a simple topic. So I have mixed number system, and also we will consider the ADC and DAC questions in that. Number systems and ADC and DAC. This is YouTube VLSI, it's a free class only, na? Next topic will be number system and ADC and DAC. I have mixed with ADC and DAC. So these are the questions that we are going to practice. Okay, thank you Payash. But it was supposed to be on Monday. In continuity, it was supposed to be on Monday. But for a seminar, I am traveling out of station tomorrow. So tomorrow, I don't have the smart board to take this. I don't have the apparatus to take this class. I'm outstation for taking a seminar in certain engineering colleges. Right. So I will take this. Somewhere in the midweek. Okay. Somewhere, stay subscribed to the channel. I will take this somewhere in the midweek, Wednesday, Thursday ke aaspas le lenge. Okay, for the 2 days at least I'm not available. Whenever I return from the seminar, I will come and take this. Okay guys? Okay, this is the next topic I will take, but it was planned for Monday, but then suddenly there's a seminar schedule. So at least 2 days I'm not available. After that I will plan. Okay. I will take my paid classes, because paid classes I have to take from laptop. So wherever I'm going for seminar, I will carry my laptop. I can take the paid class, which is at our Photon platform, but YouTube class cannot be taken from outstation. Okay, YouTube class cannot be taken. Whatever regular paid classes we have in the evening, that I will continue. Okay, but I will take this in the midweek, Wednesday, Thursday. I will float the information in the Telegram. By the time your next subject will be analog circuits by Sanjay Rathi sir. Okay, so your next subject now Next subject now, this will be there in midweek, don't worry. But your next subject now will be analog circuits. Very, very, very important. Analog circuits by Sanjay Rathi sir. But the timing for analog circuits will be night because sir is busy with several classes. The analog circuits will happen at 11 p.m. Analog circuits will happen now next for you at 11 p.m. So stay updated to the channel. Next is analog circuit starting. This will come midweek. Here randomly I will take out one slot in the midweek. Other than that, analog circuits will keep going. Okay, now for you immediately next analog circuits at 11 p.m. 11 p.m. Very important subject, analog circuits, Sanjay Rathi sir at 11 p.m. night timing. Chalo. Okay. Yeah, PDF will be uploaded in Telegram. The past 2 PDFs have been uploaded. This will be also updated today. Bye. Thank you. Stay safe. Take care. Happy Sunday. Keep studying and keep preparing hard for the examination.